Okay, welcome to the real Video 14. Okay, so it's the numbering gets a little weird now because I'm going to be making more than one video per worksheet, because what's happening is we were doing about one book chapter per worksheet, and now the philosophical arcs are getting shorter and longer at the same time. I'm expecting you to pick up a lot less from each chapter. So anyway, that's just making it harder to figure out where to make the cuts. So you may have more than one book chapter in a particular homework, and we're going to cover it more lightly. Okay, so this video 14 is meant to go with worksheet 14, and that should be clear. Okay, so we want to talk about something called linearity. Okay, this causes a lot of confusion. Maybe some of you are not confused because you've already been in some upper level math classes, but because we call lines linear functions when you're in pre-calc, then it gets very confusing when we say no, we mean actual linear functions, not like linear functions from pre-calc. Okay, so linearity, linear dependence, things like that. Versus independence. Okay, so first of all, what do we mean by linearity? Okay, first of all, let's talk about a linear function. We already talked about this. F, X, Y, Z. You take in a point and you spit out a different point. 3x minus 2y, z plus 3x, and y minus x. This is a linear function. You're taking linear components of the inputs and you're multiplying scalars onto them and adding them together. This is what linearity is all about. This is a linear map. This is a bona fide linear map. But for example, if I were to just, add something in here, if I were to say, plus 2, then this would be not a linear map. Maybe I decided to put like minus 1 over here. Now it's really, really close. It's affine. In fact, you could easily just say, all right, I'm going to put in right here a w, which is just always 1, and now all of a sudden we have a linear map again. So now it is a linear map. So it's kind of easy to patch this up, but it's a subtle thing, and it's really important to be careful with your definitions, because when you're working on these things, if you're not careful with your definitions, you'll end up with wacky results and you won't know why. Okay, so for example, let's say this: f of x is 3x plus 7 is an affine map, not linear. Okay, but f of x, if I just say f of x is equal to minus 4x over 3, is a linear map. Okay, so what does it mean to be linear? I want you to think of it this way. An action applied to some x plus an action applied to y is the same as that action applied to the quantity x plus y, which means you have to be able to add x and y, but you also have to be able to add their actions. And the adding may not be the same, but in linear algebra, plus means the same, because your input and output, the domain and range are the same, basically numbers. But here's an example. Person A weighs 100 kilograms. Person B weighs 50 kilograms. I take numbers that are easy. Okay, so if I want to convert kilograms into pounds, okay, I'm going to convert that into 220 pounds. And for 50 kilograms, I'm going to convert that into 110 pounds. Okay, And so I can add these guys and I get 330 pounds, or I could have just added these guys together and gotten 150 kilograms and then converted that down to pounds. So I'm allowed to go both ways. I can go this way, and add across, or I could add across and then convert. The fact that I can do it both ways is what it means for linearity to work. Now this doesn't work in temperature, and you can do that out. I'll do out a quick little example. It works if you have Kelvin and something else that's a scalar multiple of Kelvin, but if I have 10 degrees centigrade and plus another 10 degrees centigrade, I happen to know this is 50 Fahrenheit, so I'm using it. Okay, 50 Fahrenheit is going to be, you can't even add these guys, but this is 20 centigrade. This does not work because it actually makes no sense to add degrees in this way. It's kind of crazy. Okay, but if you were to try to do it, it doesn't work because this isn't a linear process. Okay, so that's what a linear function is. So what is linear independence? It's easier to explain linear dependence and then explain linear independence. So let's say I have a function f of x is sine of x plus cosine of x plus 4, and g of x is sine of x, and k of x is 17, then let's say q of x is equal to cosine of x. These guys are linearly dependent. They're not linearly independent because you can add some copies of some of them to get others. Now naturally it's easy to say f is linearly dependent on g, k, and q. That's true. But it's more correct to say these four are linearly dependent because I could nix any one of them and I would have a basis. Okay, it doesn't really matter which one I get rid of, then I still have linear independence. They're interrelated in some crazy way. Okay, so you could literally get rid of any one of these and recreate the missing one. Okay, since you can create any one with the remaining three, they're linearly dependent on each other. So this is a set of linearly dependent functions. Okay, so we do the same thing in matrix algebra or linear algebra. We think about vectors. So 1, 1, 0. If you prefer little brackets, you can think of them this way: 1, 1, 0. And 1, 0, 1, and let's say 0, 1, 1. These guys are linearly independent because they're made up in such a way you can't add or subtract any two of them together by any scaling in order to get the third one. They also form what's called a basis. They're not a very nice basis, but it's a basis. That means you can actually construct or make any A, B, C you want, where A, B, and C are real numbers. You can add and subtract these guys appropriately to get anything you want. So they actually form a basis, which is a separate question. Okay, so here's the point. Linearity is the ability to add items together before or after an action and get the same result. Okay, so linear independence is having a collection of non-redundant items that have this property that can be added in some meaningful way. So here's an example of linearly independent set of functions. You recognize these. It's the polynomials. Okay, so that forms the basis of polynomial functions. So here's a question. For anything in the set above, could you use multiplication to get from one to the other? You can, but if all you're permitted is addition and scaling, you can't get from one to the other. So they're linearly independent, so even though you can square them to get from one to the other. Okay? All right, now we're going to move on to what does it mean to be orthogonal? We're going to talk about sets of functions being orthogonal or orthonormal. So two different words that sound very similar, but orthonormal families are a set of orthogonal families. So let me try to draw a diagram here. So they're nested like this. In order to have orthogonality, you have to have linear independence, but you can have linearly independent basis that is not orthogonal. Like, for example, we just looked at the polynomials, the x squared, x cubed. That would be a linearly independent set, but they're not an orthogonal set, and they're not an orthonormal set. So let's add more to this definition so that we understand what makes a set of functions or vectors or anything, what makes them orthogonal or what makes them orthonormal. Okay, if a set of functions is linearly independent, what else is needed so they're orthogonal? So let phi be a set of functions, so phi 0, phi 1, phi 2, phi 3, all the way up to phi n, or it could be an infinite set. If their integrals zero out in the following manner, then the set is orthogonal. I'll tell you what W is in just a second, but you're going to integrate from A to B. You need an A and a B as part of your definition, and you need a W, it's a weight function, and then you multiply by phi of two different phis or two of the same phis. If they're two different phis, then their integral zeroes out. If they're two of the same, then they can't zero out, and that will make sense when I define what this weight function is doing. Okay, so let's figure out what this weight function is right here. I want a nice little circle. There we go. Okay, so this thing is a weight function. It's not allowed to ever be negative. It can be zero, but it can only touch down at individual points. It can't be zero on any sub-intervals. Okay, so it can have a root, but it can't go negative and it can't stay zero. Okay, that's the constraint on the weight function. And this other thing over here is pretty cool. If this guy, so it can never be zero, and that's pretty obvious from just kind of looking at it. But if it is 1, why is my circle not showing up? There we go. If it is equal to 1, it is always 1 for n equals m, then we actually have orthonormality. So orthonormality is just a little small additional constraint on top of orthogonality. Okay, and so if a set of functions is orthogonal, we get really pretty math when we try to do least squares calculations. So orthogonality makes for pretty math and LSR calculations. Okay, I'm going to give you a simple example. Okay, so are these two functions orthogonal with respect to weight functions? So little pieces you have to be aware of. You have to have a weight function, and it has to be either completely positive, or if it's zero, it can only touch down. You need your A and your B, and you need at least two functions. These functions, two or more, in the set. So we have what we need to answer the question. So now, since we only have a single set of two functions, we can go ahead and test this to see if these two guys are orthogonal. So we only have, well, okay, let me just first say this thing I never test, but I have to test it because I'm showing you the proper way. I have to make sure that the functions themselves, when squared and integrated, don't equal to 0, and that's obvious. This is just obvious. But just sanity check that nothing bad is happening. Okay, now, we're going to go ahead and check to see if the two functions, so f of x means it could be either of these, sine or cosine, and neither of them integrates to 0 when it squares, when I use square itself. So we have sine of x, cosine of x, dx, and I think this is a review question for you guys. So I'm going to let you integrate that and come back, and then I'll do it for you. Okay, hopefully you found out that was 0. If you forgot how to do this, it's u squared over 2. U is equal to sine of x, du is cosine x dx. Put all those pieces back together, you're going to get sine squared x over 2, evaluated it at 2 pi and 0, and that's going to give you 0. Yay! There. I'm just going to say orthogonal because I'm getting lazy. Okay, here's another example. Okay. Next example, show that the first three Legendre polynomials are orthogonal. They are orthogonal from -1 to 1 with weight equals 1. Okay, so first you have to sanity check. Okay, if I integrate from -1 to 1, am I going to get 0? Well, I would get 0 if I just integrated plain old x. Why does this keep happening? I want a pen, please. If I just integrated x from -1 to 1, there would be a bit of a problem. But if I square it, it's fine because it's x squared from -1 to 1 is not going to have an integral of 1. And x squared minus 1/3, when I square it, it'll stay strictly positive. So anyway, the stupid check works. Now we actually have to check the individual pairings. So here are the various integrals we need to check up on. Okay, so we only had 3 functions to start out with, so we only had 3 possible pairings, right? Because it doesn't matter which order you're in. 3 choose 2 is 3. So anyway, the first one, I'm going to see what happens when I integrate x from -1 to 1. And hopefully you understand why that's 0. I'm going to just draw this. You're going to get the pluses and the minuses canceling out, and so this is equal to 0. Okay, now we want to look at the next function, which is a little more interesting. This one is x squared minus 1/3, so the graphical explanation is a little harder on this one, so let's go for the integral explanation. X cubed over 3 minus 1/3 x, integrate, evaluate at 1 and minus 1. So you get 1/3 minus, what do we get? You do it. I mean, this is obviously 0. The only problem is you might just trip over your own negative signs. This negative sign here and here and here are all the same. I'm going to turn them all blue for you so that you can see them and understand where everything is coming from. And this minus sign is just from, well, when you integrate, you do the top minus the bottom. Okay, and so if you put 1 into x cubed over 3, you get 1/3, and if you put 1 into 1/3 times x, you get 1/3. I mean, so just work this out. And so this whole thing has to be equal to 0, so that checks out. And the final one is actually really easy if you think about it, and that's because why? Because we have an odd function, which is just x, and here we have an even function, but an even function times an odd function is an odd function. If you have an odd function from anything into the minus of the same thing, that equals 0, so that wipes out. Okay, I do have a website I want to refer you to. Let me just open that up. And I'm going to leave this for you to look at. I guess when I enlarge that, I'm not enlarging this. I'm going to copy this for you. I want you to look through this website and just enjoy it, learn from it, and that will help you in your homework. Okay, so hopefully you can see that. All right, that'll tell you more about orthogonal functions. And when you are asked, hey, do you know any other orthogonal function sets? You can say, oh yeah, because I read that website. Okay, here is an example. I guess that's an understatement. Okay, so why is this such a bear? Okay, let's talk about why this is a problem. So if you have sine of k1x times sine of k2x, and you're integrating from, whatever, minus pi to pi, 0 to 2 pi, what have you. But these guys are both odd, then there's no cute little geometric shortcut. If one of those is even, or if one of those is a cosine, you're in good business. There's all sorts of symmetries you can take advantage of, and you're going to do that in your homework. But sooner or later, you have to do the work. And in this case, we have this situation where we have no get out of jail free card. I'm going to plot these functions so you can kind of see what's happening here. Okay, because Wolfram Alpha is so much better at plotting than I am, this is what happens when you plot from 0 to 2 pi, which is what we're concerned with, sine of 3x and sine of x. We're going to multiply them, but I wanted you to see them side by side. So you can see that, well, actually, this one does have some symmetry. Okay, so let me pause for a second. Okay, so I said something that is true in a slightly different situation. So if we were integrating from 0 to pi, then there is no geometric shortcut. But notice that actually we do get this sort of flipped symmetry about pi. If we go from 0 to 2 pi, then we do have a shortcut, and we can say, hey dude, everything rotates around pi, so all the pluses have to even out with all the minuses. But actually it's not actually true, is it? Let's find out. But it's definitely not true from 0 to pi. So let's see what happens when we multiply these guys together. Aha, there we go. So here's the problem. It looked symmetric until we flipped it. And so already, so not only do we not have a shortcut from 0 to pi, we also don't have a shortcut from 0 to 2 pi even. So there's no quick and easy way to say, okay, these ups are gonna even out with these downs. Okay, so this is the nasty one, and we're gonna have to go ahead and pull out all the trig functions. So let's jump in. I'm going to come back here later. I'm just going to start working on the trig functions over here. I prefer to start with sine of a plus b and cosine of a plus b because, well, it's not a bad time to review anyway. It actually is pretty cool, and I want to show you some neat things that might get overlooked if I went to sort of a higher level formula first. There's something really powerful and subtle going on in these formulas. So here's a crazy thing. If you take any sine of, let's say, x, you can add or subtract anything you want here. You can multiply anything you want over here, and then you can add some cosine. You can add or subtract anything. They're all of the same period, so you're still going to keep the same period no matter what. So this is crazy. You have something that has a period of 2 pi over here and something that has a period of 2 pi over here. So it's clear that this whole ball of wax has to have a period of 2 pi. But what's not clear is that this is exactly another sine function or cosine. So if you think of sine and cosine as being two copies of the same thing that are shifted, and you add two copies, like you can take sine, shift it, scale it, take cosine, and it's really the same thing, right? But the point is you're taking two copies of this curve and you're adding them together. You're going to have some final function, which is c times sine or cosine, x plus some shift, and like this happens. Like this whole thing gets combined to be just another sine function shifted and scaled with the same period. And that's pretty profound. And I feel like we we really don't mention that often enough when we talk about trig functions. So I just wanted to make sure I got that out there. And if you feel your head exploding, just pause the video and listen to that again. Think about that. Try some examples on Wolfram Alpha. Don't just take my word for it. At least play with it for a little bit, because it's a little bit earth-shattering when you realize that that's true. So go ahead and let your brain explode and go play with that and come back when you're ready to hear the next thing. Okay, so because that's true, then we get these guys for free. All right, so we get 2 sine x cosine x, because all we did is let a and b equal x. And cosine of 2x, again, you just let a and b equal the same thing. Okay, and then you can do things like this. Okay, sine x plus 2x is sine of 3x. So we can just work this out. You should pause and work this out and see if you get what I get. Okay, so I'll let you do the algebra on that, and then you get 3 sine x cosine squared x. If you like imaginary numbers, go ahead and do it that way. I'm proud of you. I'm going to do it this old way because I just want to. Okay, now what if I wanted to do sine of 4x? I don't know why I said sine of 4x. I mean, we can go there. I just don't want to. So what I want to do is ask the following question. Can I take this quantity, the following quantity? Okay, I want to know if I can take sine 3x times sine of x and do something creative with it. And so I'm going to try taking this up above and multiplying by sine of x. So I get 3 sine squared of x cosine squared of x minus sine to the 4th of x. Darn. Why? Because I know that if I want to do integration on that thing, it's going to be a pain, because I still end up with really messy things. I really would like to take a single copy of sine or a single copy of cosine out, and I can't do that unless one of these exponents is odd. So I've got just more messes. So we're going to have to work with this mess. Because see, normally what I would do, and I'm going to do it anyway, I would take the cosine squared and replace it with 1 minus sine squared. But I hope I can leave like one extra cosine hanging around so I can do integration by parts. Guess it's not going to happen like that. Okay, so I can keep going, and so for sine 3x sine x, I have reduced it to 3 sine squared x minus 4 sine to the 4th x. It doesn't look like I've improved it, but I kind of have. I do have some other tricks up my sleeve. I'm going to see if I can use them. So for example, I know the following. I know that cosine of 2x is cosine squared minus sine squared of x. Okay, and then this should be cosine squared x minus 1 minus cosine squared of x, which means it's 2 cosine squared of x minus 1. Okay, then what does that tell us? Tells me I'm running out of paper. Well, luckily I can never run out of paper on this thing. I'll just run out of battery. So that means cosine of 2x plus 1 over 2 is equal to cosine squared of x, which is just brilliant, because if I have cosine squared, and I can do this for sine squared also, 1 minus cosine squared is sine squared, so that means this trick will work whether I encounter a sine squared or a cosine squared. I have a way of reducing the power on cosine or sine by a factor of 2 somehow. But the problem is we have sine to the 4th. So what do we have? We have sine to the 4th, so let's square this mess. This thing squared has to be sine to the 4th of x, which is something we have to figure out what to do with. Okay, so you may say, wait, we haven't really solved this problem because we still have a cosine squared piece, but aha! But we can think of 2x as just being like its own thing. It could be u, for example. And so this whole mess must be something we can rewrite this way, because we can still use that same formula on the 2x like we used on the x. And so I'm going to put all these pieces back together. Okay, now we finally found a way out of the forest. Okay, we have this expression for sine to the fourth, but we also need an expression for sine squared, so we're going to use this thing for sine to the fourth. I kind of wanted it in red. There we go. And I wanted to look for the expression I had for sine squared. Where was that? It's this guy. So why don't you go ahead and put those two things together and see if you get the same thing I get. This is sine squared of x, and this is sine to the fourth of x, and what we wanted to do is 3 of these guys minus 4 of those guys. Go ahead and do that and see if you get the same result I do. You didn't actually expect me to do anything with it, did you? Okay. I'll do the rest of the algebra. Here I am, partway done, and I want to do the canceling, and it's just more fun to cancel when somebody's watching. So here's 1.5, and here's negative 1.5. Woohoo! Alrighty then, and so it's pretty easy now. You can dump that back into your integral now that it's just cosines and we've disentangled this. Then the integral will be 0. You can go ahead and finish that. So whenever possible, you want to avoid doing that. For this class, you can use Wolfram Alpha, but I did want you to see that whole mess one time so you know where it all comes from. However, many times there are shortcuts, and most of the questions in your homework have shortcuts. I want you to look for the symmetries in which the resulting function is rotationally symmetric about the origin or some other useful point. Let's say it's symmetric about the midpoint of the where you are, and look for mirror imaging. Okay, so here's my favorite shortcut. I like the following. Okay, so if I need to take this integral, and there's all variations on a theme, but this is my favorite function to do this shortcut on. Okay, so first of all, we're going to sketch this thing. I'm going to sketch this thing. Okay, so when I'm sketching these things, I like to put little guide points first, and then I like to sort of put these things at a 45-degree angle, or if it's not 45, it doesn't matter as long as they're all equal. These guys are flat, so you can just sort of connect each piece. That was awful. Luckily I have an eraser. Okay, so this sketch is disgusting. Right, so I'm going to try to make it look a little nicer. And I want to show you that it's not impossible, but it's definitely not necessarily easy to get a nice sine or cosine graph. But with a little practice, you can get it to look at least that good. Okay, so now just visually, you can tell that sine squared of x is equal to 1/2 of minus cosine of 2x plus 1/2. I know we just said that. We just proved that up above. But now you can just visually see that. You can also see that sine squared plus cosine squared equals 1. How can you see that? Well, let's do the same thing again. Let's just copy this. Now you have to use your imagination, but if I had drawn this properly, there's only 2 different shapes that you're seeing here, 2 different areas. So for example, you're seeing this area up here. This shape is the same as this shape down here. And again, this is, you have to use a little bit of your artistic understanding, but those 2 shapes are really the same. And these 2 shapes are really the same. Okay, so if you can see that there's really only 2 kinds of shapes that I'm coloring here, you'll understand why sine and cosine each have to average 1/2 as you integrate them, and why when you add them together they add up to 1. So In cases where you're integrating over half a period, often, or part of a period, you just have to look and see if this holds true. And it even holds true if you shift by some amount. So like, let's say I shift by some weird amount from here to here, then I've got half of a period, but if I go from, a quarter period, but if I go from, let's say, drawing tool, let's say I'm epsilon away. Let's say I'm epsilon away. This is pi minus epsilon, and this is 2 pi minus epsilon. So still, when I integrate from pi minus epsilon to 2 pi minus epsilon, I've still got a whole cycle in there. So that function is going to average to be 1/2. So when I'm doing this, I make it look all willy-nilly like I don't know what I'm doing, and I just say, well, sine is the same as 1/2, right? And then I can just go pi over 2 times 1/2 is pi over 4, and it looks really cool, and it looks like I'm just sort of using black magic, and I get the right answer. But the point is, you have to know what's happening under the hood, and that allows you all this freedom as long as you have some kind of symmetry, or you have some kind of, you know what's going on, and you know what's going on with the periodicity. Okay? Alrighty, Fourier sine and cosine series. Claim. From minus pi to pi with a weighting function of 1, the set of sines and cosines together with the function 1 is an orthogonal family. And we can use this following process that I'm going to tell you to estimate f of x over minus pi to pi using a linear combination of this family. And let me say, before I give you that explanation, if you want more details, this is a really good explanation. It's I've never heard of this guy, Jeremy Orloff, but I like how he writes, and he explains all the main ideas that anybody would give in a standard lecture on the topic. We're just going to kind of hit the surface. We're not going to go into as much depth as he does, but it's very fascinating, and there's a lot of interesting things I'd love for you to read about. But I'm not going to test you on it. But that's a great next step to learn more. Okay, but I'm going to tell you what this process is. Oh, there's a second paper I want to show you as well. Hold on a second. This is another great explanation, and it is scaled back a little bit with, so it's pour tout means for all. So there's a sort of mixing of languages in this website, so it's okay. Hopefully you're able to read through this. But these are two great resources to help expand your understanding of what's going on with this topic. Okay, so the process. Okay, so the function f of x can be approximated from minus pi to pi. Okay, you can change that, but it's easier to just pick an a and b for a definition here. Okay, f of x is a naught over 2 plus a1 cosine x plus b1 sine x plus a2 cosine of 2x, and so on and so forth, where the following integrals tell you what the linear weights are on those functions. Please note that this one is redundant on purpose, but it's just sometimes people list it. Obviously, if cosine of 0 is 1, then you don't really need to write this, okay? But you can write it in there. The other thing to notice is that in keeping with the convention in burden and pairs, I am putting a cosine up 1 power more than the highest power of sine. So I'm making pairs of sine and cosine, and the reason for this is rather subtle, and that's because actually we should be using complex analysis, and this is, you can think of this as essentially being the partner for this guy, and it also explains why there's a divided by 2. It's very bizarre. So the weirdness that this formula appears to have goes away completely if you just do this in complex, using complex coefficients. I don't want to do that right now, okay? But it is a fun thing to do. Okay, so let's do an example. All right, I'm going to squish this so that we can keep seeing it, because I need you to see it for this next example. So hopefully you can still read that. And I'm going to ask you the following question. Give the Fourier coefficient, Fourier coefficients for f of x equals 3 sine of x plus 2 sine of 3x minus 4 cosine of 8x. Okay, so this is meant to just see if you're paying attention, and the answer would be what? Answer is what coefficient goes on sine of x? Well, sine of x is b1, so b1 equals 3, right? And what coefficient goes on sine of 3x? Well, that would be b3 must be 2, and cosine of 8x, well, that would be cosine of 8x would be a8 must be negative 4, and then the rest are equal to 0. So that's just doing the problem backwards. I mean, this is just matching the pieces, and I wanted you to know that that's totally fair game, and that's a completely valid exercise. Okay, so next what we're going to do is we're going to say, actually give the Fourier expansion for something more interesting. Okay, I'm going to ask for give Fourier sine and cosine series expansion for f of x equals just plain old x, okay, over, you know, over whatever we have already defined. Okay, notice f of x is odd, so this is odd. So as a bonus, odd function, why don't you tell me which terms? Is it all the a's or all the b's? Which part is going to wipe out? Pause this and think about it and tell me what wipes out. Okay, so we're only going to use sines, because here's what happens for any cosines. Cosine of who cares, and cosine itself is even, right? And then this is odd. Cosines is even, and so the resulting function is odd from minus pi to pi, so that's 0. So in this example, we're only going to have to worry about the sines. All right, so let's go ahead and do something about that. If we're lucky, we can just do them all at once. Let's see if that works. So bn, I'm just going to rewrite it. It's going to be no easier, no harder this way, but just I kind of get annoyed when I'm doing the same integral twice. So I'm just going to go from 0 to pi and double this x sine of n pi dx, and I'm going to take this piece off to the side and work on it. I'm going to take the following. Integral is x sine of nx dx, and then I'll take this result back and we'll bring it back to the previous page. So I got rid of the limits and I got rid of the thing outside. So I got u is equal to x. Everybody does integration by parts a little differently, so you can go ahead and do it your own way and see if you get the same thing I did. All right, and I'm going to say v equals minus cosine of nx over n, and so this becomes, in my notation, uv minus integral v du, so I get minus, I get minus x cosine of nx over n. That was messy. Minus x, why is this always a mess? Minus x, there we go. Cosine nx over, it's not even straight. I hate that. Minus n, okay, plus integral cosine nx all over n dx. Okay. All right. So does this help us? So the integral, if we do that last integral, because now we can, plus sine nx over n plus c. And here's my advice. Do by hand. Do integrals by hand. Check on Wolfram alpha or some other technological way of checking that. That's my advice. Okay, so we're going to take this piece back to where we came from, and since it's a definite integral, I don't need to take the plus c. It doesn't matter. I'm going to copy this and bring it back to the previous page. Okay, there I go. And so I'm going to just adjust that location a little bit. There we go. So that goes from pi to 0, and you're multiplying outside by 2 over pi. Okay, and I'll let you do that yourself. Okay, I think you can handle that. And that's 2 over pi after you do out all the pieces minus pi over n cosine of n pi. And you may think, aha, there, I'm done. But I'm not, because actually there's another thing I want you to do. Let's talk about that. Notice when you do sine of n pi, that is always 0, where n is an integer, right? So you're going to ding, 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 ding. You're going to go at 2 pi, at pi. At every integer, that's going to be equal to 0. So that, if we got sine of n pi, we would replace that with 0 as long as n means an integer. But that's not what happens for cosine of n pi. Cosine of n pi has a different pattern, and what happens to cosine of n pi is it goes positive 1, negative 1, positive 1, negative 1. So when x is equal to even, it gives you a positive 1. When x is equal to 1 or odd, it's going to give you negative 1. So it's like negative 1 to the power of n. So we're going to replace, whenever we see cosine of n pi, this is standard stunt, you've probably seen it before. I'm going to replace cosine of n pi with minus 1 to the n. Okay, so I'm going to just dig in here very gently and erase my cosine of n pi and replace it with minus 1 to the n. And I know there's a negative outside. That's kind of annoying, but that's just the way it is. And oh, also this pi cancels out with this pi, which is kind of cool. So bn is equal to 2 over n, so minus 2 over n times minus 1 to the n. Okay, so a n equals 0, and bn is equal to that, gives the Fourier coefficients for f of x from minus pi to pi. Okay, so you know you can check your work online. Okay, this isn't the best. Sometimes I can coax Wolfram alpha into giving me some of these coefficients, not always. So symbollab.com works fairly well. If it doesn't give you the answer, it at least sets up the integrals correctly for you. So give it a whirl, see if it helps you at all. So parting thoughts, you might not be able to see that URL. Let me just copy that and put this down here where you can see it. Hopefully you can see that. So some parting thoughts. Any orthogonal family of functions can be used as a basis for expressing other functions. It is totally crazy, but it is totally true. We are only focusing right now on Fourier sine and cosine, but there is a whole world out there, and this is truly just the tip of the iceberg.